Hey there, this is Tom Odin, and this is my CSC594 project. So, I chose to focus on the problem of parsing recipe data. And the motivation for this was an application called Chefly, and Chefly was developed by myself and 5 other students for our SE491 and 591 course, Software Engineering Studio. And what we wanted to do was make an application for Android that would allow cooks to cook with voice interaction, sort of like Google Home or Amazon Alexa, so that they're not printing out recipes or looking at pieces of paper or looking at them on their phone or iPad and getting bacteria or water on their screen. So to serve them recipes, we found an API called Spoonacular. Spoonacular has um, a store of about 300,000 recipes with pictures, and we've liked it so far, but are looking for a change. Spoonacular has some drawbacks that it costs money, and we're starting to come up on the end of our free subscription. And we also see some issues with format and quality of those recipes that they serve. Sometimes the instructions ramble on, and that's not good when you're trying to relay like one instruction at a time to the user, or the quality of the recipe. We don't have much autonomy when it comes to inserting our own recipes into the API. So we've been looking at rolling our own tool, and we've been wondering, is there a way to parse recipe data from the internet? And writing a web scraper to grab HTML of recipes shouldn't be that hard, but taking that data and putting it into a consistent structure is more difficult. So that's the question I tried to answer, and it turned out that the New York Times cooking team also tried answering that question, and they pointed to a paper that defined that issue as a structured prediction problem. And a structured prediction problem involves classifying multivariate data with large sets of input features. And if you think about recipes, they have different facets in terms of the ingredients and how the ingredients are listed, the length, and also the instructions, so that it's multivariate and has different input features. And so I think that fits the problem. So what they did was look at a paper by Sutton and McCallum, and that's the main thing I based most of this presentation off of, that introduced a model called conditional random fields, or CRFs. And CRFs are a graph-based model. You're navigating through paths in a graph to find the most likely sequence, and it yields a conditional probability. That's important. Conditional probability um, deals with whether a sequence Y is output given an input X, rather than the likelihood of X and Y occurring. That's more of a joint probability. So conditional random fields have a lot in common with structures we have looked at in class and in other models. One would be naive Bayes, that it's a graph-based algorithm. Another would be logistic regression, or maximum entropy model, in that they utilize feature functions and they yield conditional probability. And they also share a lot with hidden Markov models, in that the algorithm is very similar to the Viterbi algorithm, and they yield a sequence-based model, like how we considered the number of hot and cold days, the sequence of hot and cold days given the sequence of ice creams eaten. So now we're considering the sequence of recipe tags based off input phrases. So it's kind of hard to conceptualize with words alone, so hopefully this visualization gives you a better idea of the relationship between different models. So here you have naive Bayes. It's a directed acyclic graph, and if you add in those feature functions I talked about before, I'll get to later, and yield a conditional probability, then you have logistic regression. And naive Bayes and logistic regression are classification algorithms. You yield one classification variable, but if those variables become a sequence, if naive Bayes turns that into a hidden Markov model, but if you incorporate those feature functions of logistic regression into a sequence, you have linear chain CRFs. We're going to ignore the general applications of those for now. We'll move on to the application towards recipes. So when you think about the features of a recipe ingredient, there's a lot of inner features. Think about a name, a unit, a quantity, a comment, or another remark. So even looking at a phrase like 2 red onions peeled and diced, obviously 2 is a quantity and red onions is a name, but what about peeled and diced? That could be a comment, that could be other. Maybe red onions peeled and diced is a name, and there's not really a unit apparent. Red onions could be a unit. These are things that a model would need to determine. These models are aided by feature functions. So when I showed you that graphical model, these smaller nodes amongst the larger ones represent feature functions, and those are designed to help encourage likely predictions. So if you think about Markov models where the next event is only dependent on the one before it, think about y being a tag and x being the input. So let's say the input is 1/2 and the tag the model comes up with is quantity. We really want to encourage that because 1/2 is not going to be a name or a unit. So we want to assign that a probability of 1. And if our model for some reason thinks that's not the case, we'll assign it 0 to give it a very low probability. And hopefully that'll steer it away from that sequence that it builds. Another example might be, let's say the y, the tag, is quantity, and the tag preceding it is unit. Well, if you think about a recipe ingredient, quantity and unit are almost always right next to each other. So we'll encourage that probability by assigning it 1 as well, and 0 if it's not the case. So feature functions help encourage likely predictions that we want to happen. So when you build feature functions like those, and you can make hundreds of them, you're going to get some strong results. The New York Times tagged 130,000 different ingredient phrases and trained their model based off of them, and then tested their model on 481 phrases because they also had to hand tag these, and ended up with about an 89% accuracy using conditional random fields as their model. They didn't reinvent the wheel and write their own algorithm either. They used a library called CRF++, and there are other libraries out there. Another one's Mallet, that's a heavier library with more NLP tools than just CRFs. And I saw at least 9 or 10 other open source CRF libraries out there, so I encourage you to use CRFs, but also not necessarily write your own model. Go out and use another open source one. This is only the first half of my research paper. I looked at other models and seeing if they're better, and one that came across was named entity recognition. In the comments of the New York Times article, ironically enough, the author of Spoonacular's algorithm stated, "Hey, I wrote my PhD thesis about named entity recognition," and so I started looking at that approach and realized that CRFs and named entity recognition share some approaches, in fact, and then also have some different ones. Like named entity recognition could also use a maximum entropy Markov model instead of CRFs. So from what I've seen so far, maybe the best application of these might be to use CRFs on the ingredient phrases, and named entity recognition, which it is more focused on names in the context of phrases, might be best for using within recipe instructions. So as I continue on, I might write more about how to combine those approaches for a comprehensive tool. But anyway, I'd like to thank you for watching my presentation. I've enjoyed this class and looking into this problem, and I hope this is another tool you can put in your pocket for future NLP endeavors. Thanks a lot.